Alright, so our very last conic section is the hyperbola. So we started with circles, then we went on to parabolas, both of which were new, but were reviewed. And then now we're on to, or then we did ellipses, and our last one is a hyperbola. So a hyperbola looks something, so here's your axes. I'm just going to put my center here in the middle for now. But it's something like this, where you can think of it as two parabolas together, but going in opposite directions. In a hyperbola, we have our center, which is still HK. We call this distance between the center and the vertices is A. And you also will have two foci. And just like in the parabola, they're going to be on the inside of your curves. So when it comes to the standard form of what this looks like, you have x minus h squared over a squared minus y minus k squared over b squared equals 1. So our standard form is a lot like the ellipse, except with a minus instead of a plus. Where this a that goes between the center and your vertice of your hyperbola is the square root of this number under x. Now something else that we also have with hyperbolas, and this helps tell us how big the hyperbola is we have asymptotes. And these asymptotes are your slope. It's going to be x equals y equals, not x equals, y equals b over a times x. So this is where that b would come in. So this is your rise because it's under the y, and you have your run under the a. Now if we were to switch the direction of our hyperbola, so let's say we wanted it to go up and down. How that would change your standard form is you'd have y minus k first over b squared minus x minus h squared over a squared equals 1. Where this distance would be your b between the center and your vertices. You would still have asymptotes, that does not change, and it would still be b over a times x. Just like in before, we will have our foci, or foci, and we have a formula for the focal length that helps us find this distance of f. So that distance there is f. The focal length, and this goes for both, no matter which direction you have, is f squared equals a squared plus b squared. So it's similar to the focal length that we had for an ellipse, except we don't have to do the absolute values because it's a plus instead of a minus. Whereas in the ellipse, it was a subtraction, which meant we needed to have the absolute values to assure we got a positive number. Now, we do have some special names that are different for a hyperbola. This distance between your vertices, so from here to here, this is called the transverse axis. The transverse axis the distance between the vertices. We also have something called the conjugate axis. Now the conjugate axis would be on here. If I were to go up and down B, whatever B is, this length here, this would be called the conjugate axis. I just realized you can't see that. So this here, so A was our vertices, this would be the transverse. Our conjugate would be the one that goes from B to B, or B to negative B, since we're centered around 0, 0. So the conjugate axis is the distance between points that are not vertices. So in an ellipse, we called them covertices. In a hyperbola, they're not vertices, but they are points that give us the length of the conjugate axis. The last thing that we kind of need to know is our general equation for asymptotes. So up here, I gave you the equation if it was centered at 0, 0. But it's not always going to be centered at 0, 0. So when we're not at 0, 0, we go to our point slope form. Where x1, y1 is the center. So this allows it to be anywhere on your graph, not 0, 0. And then your slope is going to be b over a, where b is the number under under y, and a is the number under x, or the square roots of the numbers under y and x. But writing it this way would allow us to move our center outside of the origin, and we can still find it. So these are all the key pieces to a hyperbola. They're very similar to those of an ellipse, and that's where these can get a little difficult because we're going to be trying to tell the difference without knowing the shape. And we're going to talk about that tomorrow, actually. How to look at these and know what shape we have, if we have a hyperbola and which equations go with it and all that. But for right now, we're just going to practice graphing one of these and finding the pieces of information that are necessary. And we are going to do this for a couple of days, so if it's still a little fuzzy, that's okay. We're going to do this tomorrow and on Friday. So our one example we're going to do, excuse me, we're going to find the center the vertices, the foci, and the equation for the asymptotes. And I just realized something that I didn't mention. On our slope, we have to do both the positive and the negative to get both directions. So you're always going to have the plus minus of your b over a for your slope, so that way you get both asymptotes. And the length of the transverse and conjugate axes. Alright, so we've got a lot to find here. So our equation that we're going to do is y minus 3 squared over 4 minus x plus 1 squared over 36 equals 1. And I'm going to come over here and just draw a set of axes so I have room. So for the center, we can read that straight from the equation. It's our hk, so h, remember, is with x, k is with y. So our h will be -1, comma, k is 3. So I can come over here to my graph, -1, 3, there's my center. My vertices, so because y is first, I know that my vertices are going to be going vertically because it's y is first. If x was first, they'd be going horizontally. So from here, I'm going to go up 2. So here's center, here's a vertice, down 2, here's another vertice. So that's going to be at -1, comma 5 and -1, comma 1. Those would be my two vertices. For the foci, we do have to do a little bit of work to find the focal length. So I know that f squared will equal a squared, which in this case is 36. So here's our a, here's our b, plus 4. So we have the square root of 40 equals f. So when I go, again, I'm adding it to the center. So my focus is going to be square root 40 up and square root 40 down. So square root 40 is it's between 6 and 7. So between 6 and 7, I'm going to be way up here. So 1, 2, so I'm just going to estimate it because it's going to go off my graph. And so I'll try to estimate the same rough distance. So when we come to write our points, we added these and subtracted from the y value. So we'll have -1, comma 3 plus. So square root 40 simplifies to 2 root 10. And -1, comma 3 minus 2 root 10. And those would give us our two ordered pairs. So then the last thing that we really need to be able to graph this are the asymptotes, because those are going to guide how wide or narrow of a graph we're going to draw. So for our, let's see, for the asymptotes, the equations you can find by doing y minus, now our center was -1, 3, so y minus 3 equals our slope, which in this case would be b over a, so 2 over 6, which reduces to 1/3, so plus or minus 1/3 x plus 1. So these would be the equations of our asymptotes. That's great and all, but I'm going to show you also kind of a shortcut for graphing this without having to solve for y and all that. So we already know that we already have our vertices plotted. So if we go and think of the conjugate axis, because we do have to find that length, if we were to go from our center, so that's 1, 2, 3, 4, 5, 6. So that's 6 over to the right. 1, 2, 3, 4, 5, 6. And 6 over to the left. You'd get your non-vertices, but you'd get the endpoints of your conjugate axis. If you were to take your vertices and draw a box where each of these conjugate and transverse axes divide your circle, because here's your transverse, here's your conjugate axes. These endpoints are part of your asymptote. So you'd be able to just sketch these through the center, through the endpoints of that box, and you have your asymptotes without actually having to find the equations. Now, because it asked us to find them, we needed to, but if it doesn't ask you to, you can always just draw this box by taking your vertices and then the endpoints of your conjugate axis, which we find by the square root of this number, and then just connecting them in a box where each of these points is in the middle of a side. Then the corners are 2 points that are going to be on your asymptote. And so what that's telling me is that I have a hyperbola that's going to go something like this, that's rather wide. Now the last bit that we haven't answered is it did want to know the length of the transverse and the length of the conjugate. So our transverse so from the center we went up 2, down 2, so that would be 2 plus 2 is 4. The conjugate, we went 6 to the right, 6 to the left, so add those together. Your conjugate axis is 12. The conjugate and transverse axes are really there to just help you sketch your graph a little bit quicker without having to find the equations, but you can also use the equation and graph that as well if that's something you would rather do. Because if you had done this, you would have had up 1 over 1, 2, 3. You would have gotten that point there, which is another, you can see is on our asymptote. There's a lot of ways you can do your asymptotes. It's just a matter of which one do you remember and which one do you want to use. We are going to do another one in class tomorrow to make sure that you guys have graphing down. It's really similar to the other ones. It's just where the pieces all go and how the graph looks. The major addition here is the asymptotes and the transverse and conjugate lengths, but how we find the center and the vertices and the foci are pretty similar to what we've done with ellipses. So come with questions. Like I said, we're going to do another one in class just to make sure. And then on Friday is when we'll look at the going backwards, the writing the equations. So yeah, please let me know what questions you have so that way we can get them all figured out.